Okay, so we have a new topic today, which is greedy algorithms. But before we start on that, just one quick announcement, which is that this week's homework is, perhaps a little bit more challenging than the previous one. And so hopefully you've already got started on it. But regardless, the due date is now Friday instead of Wednesday. Okay, just to give you a little bit more time to work through it. So, any questions about just administrative aspects of the class? Okay, so let's start with greedy algorithms then. Okay, so we're now moving on from graph algorithms. So one of the first things we looked at when we were talking about graphs was reachability, and that is a decision problem. Is node T reachable from S or not? Yes or no? Okay. But since then, we've moved on to problems where the answer is not yes, no, but it's a number, and we want the best number. Okay, so we don't just want to know, is there a path from S to T? We want to know what's the shortest path. Okay, and for the rest of the class, we will mostly be looking at optimization problems. Okay, what is the shortest path? What is the lightest spanning tree? What is the maximum flow? Okay, so these are problems in which we are trying to maximize or minimize something. Okay, so in specifying an optimization problem, there are these four components, okay, by which we can formally describe the problem. The first is the instance. Okay, so what do inputs look like? Okay, um, what is the solution going to look like? Okay, so the output of the algorithm, what does it look like? What are the constraints that that output has to satisfy? And finally, what is the thing that we're trying to maximize or minimize? Okay, so let's look at a little example. So we've talked about the shortest path problem. In order to formally specify, we need to put down these four things. Okay, so what is the instance? Well, we have a graph. And for shortest paths, we're typically going to have edge weights as well. And so far, we've been assuming that the edge weights are positive. Okay, so let's say positive edge lengths. And we want to find the shortest path from some node to some other. Okay, okay, so that's what the instance looks like. That's what the input is going to look like. The solution format is what does the output look like? So the algorithm's going to output something, and in this case, we wanted to output a path. Okay, so a sequence of edges. So it'll output a sequence of edges. What is the constraint? Well, the only constraint really is that these edges should take us from S to T. And what is the thing we're trying to optimize? In this case, we want the path to be as short as possible. So we want to minimize the sum of these lengths. Okay, so any questions about that? This is how we would write the shortest path problem in this particular format, okay, in terms of these four quantities. And this fully specifies the problem, tells us what the input looks like, what the output looks like, any constraints the output has to satisfy, and the thing that we're trying to optimize. Okay, and so we'll try to stick to this format when we're describing optimization problems, and we'll be looking at just a huge range of problems of this type. Okay, okay, so this is what I just put down. So in general, in these optimization problems, the search space, so what that means is the space of possible solutions, solutions that have the right format, is typically going to be exponentially large. Okay, so for example, we talked about the shortest path problem. In general, there could be exponentially many paths from S to T. Okay, so for instance, let's say the graph has S and T, and then it looks like this. Okay, and so the number of paths here is going to be, so over here we have a binary choice. Do we want to go up or down? And over here we have another binary choice. Do we want to go up or down? And just by having a succession of these choices, we can get exponentially many paths. Okay, so if we have, say, 10 such choices, then we immediately have 2 to the 10, which is over 1,000 paths. Okay, and so could easily have 2 to the omega n paths from S to T. Okay, so this is an interesting situation. The number of paths from S to T is exponential, and we want to find the very shortest path. Okay, so there's an exponential search space, and we want to find the shortest thing in that search space. It's literally like a needle in a haystack. Okay, and a lot of the other optimization problems that we'll be looking at have the same feature, that we want to find the best solution out of exponentially many possibilities. Okay, so for example, maybe the search space consists of ordering of the vertices. Okay, so if we have n vertices, how many different orderings are there? n factorial, excellent. Okay, which is which really bad. Okay, so exponential. The number of cycles of a graph could again be exponential for the same reason as this. Okay, the number of spanning trees of a graph will in general be exponential. Okay, so we want to find the lightest spanning tree. We want to find the lightest tree amongst these exponentially many possibilities. Okay, so okay, so how do we solve these kinds of problems in general? So one naive approach, the brute force approach, is to say, well, we have a search space of all these possible solutions. And we also have a criterion that we are trying to minimize or maximize. So let's just go through the entire search space and evaluate the criterion and each possible solution. Okay. But since there are exponentially many solutions, this is going to be very slow. Okay, so that is, for example, that would involve solving the shortest path problem by enumerating every possible path from S to T, computing the length of the path, and then looking at the shortest path found in this way. Okay, and so something that took exponential time. But we were able to come up with the answer much faster than this. We didn't have to look at all possible paths from S to T. Okay, so we did it in a slightly different way. We broke the problem down into subproblems. Okay, so we said rather than looking for an entire path in one fell swoop, let's build up the path slowly. Okay, and so we made a lot of smaller, we thought of the path as consisting of a bunch of smaller pieces. Okay, and we said, well, let's first try to figure out the initial portion of the path. And once we're satisfied with that, then we can grow it some more and some more and some more. Okay. And this is going to be a typical approach for solving optimization problems. We have these exponentially many structures, or these exponentially many possible outputs. We want to find the best output. Rather than looking at these outputs, which are paths or cycles or trees, as these monolithic structures, we're going to build them up piece by piece. Okay, so rather than saying, let's look at entire trees and find the best one, we'll say, okay, well, let's actually build up a tree. We'll put in the first piece, and then we'll put in the second piece, and so on. And so we'll think of this overall solution as being composed of a bunch of smaller local solutions. Right? Now, sometimes we can build up a solution by just saying, well, what's the first piece? What's the most obvious first piece to put in? Okay, and not worrying about what comes further downstream. Okay, and then what's the next obvious piece to put in? Okay, fix those two. What's the next obvious piece to put in? What's the next obvious piece to put in? And sometimes this actually works. Okay, and this is called the greedy method. And also, a lot of the time, perhaps most of the time, it doesn't work. Okay, so so this is a very important algorithmic strategy. When it works, it gives us very simple, efficient algorithms. Okay, but we also have to be very careful because this is a strategy that very often doesn't work. And so we're going to spend the next couple of weeks trying to figure out exactly how to think about greedy algorithms and looking at systematic ways of thinking about these algorithms. Okay. So here's a question. Is Dijkstra a greedy algorithm? Okay, so that's a great question. Okay, so it is, so it's not going to be as greedy as some of the algorithms that we'll be looking at. Okay, it can be construed as a greedy algorithm. This is something that is, um, this is something that is actually debatable. Okay. Um, okay. But yes, you can think of it as a sort of greedy scheme. Okay. Right. So you can think of it as sort of greedily adding one node at a time to the explored set, and but it's a sort of yes. Okay. So that's the sense in which we would think of it as greedy. Yeah. So that's a great question. Okay. So it's a slightly more thoughtful greedy scheme than some of the algorithms we'll be looking at soon. Okay, great. Okay, and after we talk about greedy algorithms, we'll look at many other algorithmic design paradigms that also have this property that rather than looking at complete solutions, um, in one go, we're going to try and build up the solution piece by piece. And there are many different ways of doing this. And techniques are going to involve things like dynamic programming and hill climbing. Okay. Okay, so let's get started with greedy. And we'll start with this little example. So this is the cookie monster here, and you can see a picture of him with his plate of cookies. But in terms of the problem we're trying to solve, okay, here's the problem. So you are the cookie monster, and in front of you is this 6x6 tray of freshly baked cookies. Okay, now they're all chocolate chip, and they're not exactly the same size. Okay, there are some discrepancies in size. Some of the cookies are small, some of them are large. Now you are allowed to take 6 cookies. Okay, which 6 would you choose? Okay, you're allowed to choose any 6 you like, and you want to maximize just the total amount of cookie that you are consuming. Okay, and the goal is to come up with an algorithm for this. So any questions about the setup? Okay, great. So this is an optimization problem. So let's start by trying to write it in our standard template. Okay, so the instance here, the instance consists of this 6x6 array of cookie sizes. Okay, so a numeric array, let's call it C. So C 1 to 6, comma 1 to 6. Okay, so a numeric array of cookie sizes, that's our input. And the solution format is going to consist of 6 cookies. Okay, so 6 locations in the array. Let's say we call them I1, J1, all the way to I6, J6. Okay, so each of them is a location in the array. What are the constraints? Well, they have to be distinct. Okay, you can't take, if there's one biggest cookie, you can't take that one cookie 6 times. Okay, the locations must be distinct. And other than that, our objective is to just maximize the total amount of cookie. Okay, any questions about that? So this is our cookie tray problem. This is how we would write it down formally. Okay. So what do you think we should do? How should we solve this problem? Which 6 cookies should the cookie monster take? How many possible solutions are there? What is the size of this search space? So there are 36 choices for one cookie. So the total number, the size of the solution space, so size of search space is 36 choose 6. Okay, so there are 36 cookies and you can choose any 6 of them. So this is how many possibilities there are. There are lots of them. Okay. But there's a nice simple algorithm. And so what should we do? What's a good greedy approach that will work well in this case? Always pick the biggest cookie. Perfect. Okay. Always pick the biggest cookie. Okay. And so we'll build up our solution by taking one cookie at a time greedily. We just keep picking the biggest one out of those remaining. Okay, so what's the first cookie that we're going to take in this particular example? 99. What's the next one? 97. And then let's see, we have I guess we have a 94 over here. Let's see, we also have a 92. What's the next one? An 88, and I guess the next one is 85. Okay, so what do you think? Is this the optimal solution? Okay, so here's a question. Would it be faster just to quick sort in decreasing order and then pick the first six? Right. Yeah, so just picking the largest one is how long does it, suppose you have, I guess, look, this input, it has size 36, right? And so because the input is constant size, anything you do on it takes constant time. But what if we had n cookies in total and we wanted to pick six of them? How long would it take? 6n, that's right, okay? Because how long does it take to find the largest cookie? You have to go through the entire list and find the biggest one, that's n, and then you do that 6 times, so it would be 6n. Okay, great. So this, okay, so the first thing is, this is a greedy strategy, okay? So rather than looking at an entire batch of 6 cookies at a time, we're building up the solution 1 cookie at a time. We first choose 1 cookie, and then we fix that. We're not going to go back. We're not going to backtrack. Okay, so we fix the first cookie, then we pick the next one, we fix it, then we pick the next one, we fix it, and so on. And at each time, we just make the greediest possible decision. We just pick the biggest one out of what's remaining. And this is going to be the best solution, right? Does that make sense? Okay. And in this case, the solution, okay, so that's the solution we got, and the total amount of cookie that we get is 555. Okay, so that is the best solution. Okay, can we build a max heap and choose the maximum ones? Yes, we could certainly do that too. Absolutely. Okay. But in this case, remember that the running time, because we have a constant number of cookies, if we're choosing a constant number of cookies out of n, the running time is just O of n. Okay. Now we introduce a constraint. Okay. Suppose you're only allowed to choose 1 cookie from each row. What would you do now? What is the size of the search space now? So you're only allowed 1 cookie per row. Okay, so you're still going to take 6 cookies, but now there's 1 per row. So what is the size of the search space? How many choices for the first row? 6. How many choices for the second row? 6. How many choices for the third row? 6. So what is the total number of choices? 6 to the 6. Okay, so it's a different search space from before. There are fewer possibilities. Okay, so previously we had more options. Now it's more constrained. We're told that we're only allowed 1 cookie per row. But once again, we're going to do a greedy algorithm. And so what do you think we should do now? What's a good greedy strategy in this case? Largest cookie in each row. That's right. So pick the largest cookie from any from the remaining rows. Okay, so again, we start with the 99 since that's the largest, but once we choose the 99, then we got to eliminate that row. And so the next one we pick is the largest one remaining, which is an 85. And then we eliminate that row. And then we choose the largest one remaining, which is, I guess, an 80. And then we choose the largest of what's left, which I believe is the 76 over here. And then we would choose the 73. And then we would choose the 68. And that would be our solution. Okay. Any questions about that? And right, okay, so right, as many of you have pointed out, yeah, we can just start with row one. We're going to get exactly one cookie per row. And so we can just start with the row one and pick the largest thing in that row, then move to row two, pick the largest thing in that row, and so on. Okay. Okay, so everybody satisfied with just what the problem is, what the size of the search space is, and what the algorithm is going to be. Okay, and it's a greedy strategy. Okay, and if we do that, we get this much cookie, 481. Okay, let's see. So here's a question. How would you know when a row ends and starts in the array? Okay, so our array is just in this format. So each row I is of the form CI1 all the way to CI6. Those are the elements of row I. Okay, and so we pick the largest out of that row. Okay, so let's go ahead and write down this modified version of the problem using our standard template. Okay, so numeric array. And again, it's of the same size, 1 to 6, 1 to 6. The solution format is again the same. Okay, so 6 locations, I1, J1 through I6, J6. The constraints now are different. We don't just insist that the locations be different, but that the rows are different. So I1 through I6 are all different. Okay, so they're all different rows, but the objective is the same. We want to maximize the sum of the total amount of cookie that we're getting. Okay, we want to maximize the total amount of cookie. Okay, so questions about how we've taken our problem and just written it in this particular format. So hopefully this seems like it wouldn't be too daunting to do. You know, if you were given a problem and told, look, this is an optimization problem, can you write it down using these 4 quantities? Okay, hopefully that seems like that would be doable. Okay, great. And now we've seen an algorithm for that. Okay. Now let's look at yet another version of the problem. Suppose you're told that you cannot select any 2 cookies from the same row or column. Okay, so 1 per row and 1 per column. Okay, what do you think is the size of the solution space now? Okay, I see Dadian is saying 6 factorial. That's correct. Okay, so 6 on the first row you have 6 choices. Okay, you choose something and that eliminates a column. So on the second row you have 5 choices, and on the third row you have 4 choices, and so on. And so it's 6 factorial. Okay, so any questions about that? So it's still a very large search space. Okay, if instead of 6 by 6, this was n by n, this would be n factorial, which is exponential. So it's a huge search space. There's no way we want to look through all possible solutions. We want to do something more intelligent. So let's see. Alec is saying, is this all permutations of 6 objects? Exactly, right. 6 factorial. So what do you think is a good greedy strategy now? How should we do this one? So initially our strategy, when we had no constraints, we said, just take the biggest cookie, okay, and just take the biggest cookie remaining. Then when we were given a row constraint, we said, well, just take the biggest cookie remaining, but remove that row, okay? Now, let's see, so Margot is suggesting just take the biggest cookie remaining and remove both the row and the column. Okay, so here's a greedy strategy. That's great. Pick biggest cookie remaining and remove that row and column. Okay, so in this case, which one would we start with? 99. And the minute we did that, we would have to remove that row and column. And so which one would we take next? 81. Okay, and so on. So that would be a greedy strategy. What do you think? Is this going to be good or not? Is this going to give us the best solution? Yeah, somehow I don't have a good feeling about this. Okay, so okay, so let's go. So you start by picking 99. You eliminate that row and column, and then you keep going. Okay, and so we're going to evaluate this, but before we get to that, let's go ahead and formalize this problem. Okay, so once again, we have a numeric array. And once again, we have 6 locations. The solution just consists of 6 cookies. And this time the constraints are the I1 through I6 are distinct, and J1 through J6 are distinct as well. So the constraint changes, but the objective, as always, is just to maximize the total amount of cookie. Okay, so the only thing that's been changing for us is the constraints in each case. Okay, so any question about the formalization over here? Everything's the same, only the constraints have been changing. Okay, so using our greedy strategy, let's see. So we did 99 first. That eliminated this row and column. Then we picked 81. Then the next one that we pick is, I think 74, I guess. 74. And then the next one is, what do we do next? 60? Yeah, I guess that's right, 60. And then what comes next? 50, I guess. And finally, we're left with just one choice. Okay, so this is the solution that we get. 99 plus, yeah, so this is the solution we've ended up with. Okay. And yeah, this doesn't seem like it would be optimal. Okay, so here's the solution we got in the end. And so the total amount of cookie we got was 404. Okay, this is what our greedy algorithm gave us. Um, and Junxian's pointing out that, yeah, it seems like there might be better solutions. Yeah. Okay, but here's another solution, which is not what the greedy algorithm gave us. Remember, the greedy algorithm is completely deterministic. Okay, so I see. It's an error 404. Yes, yes. So yeah, so the greedy algorithm is deterministic, and that's what greedy gave us. But here's a better solution, different from the one that greedy gave us, and and it does better. Okay, and here's yet another solution that's much better. Okay, and this may or may not be the best solution. Okay, so this is the greedy solution. And these are better solutions. And if you look at this one over here, you can see that it doesn't, the highest valued cookie it takes is 92. It skips 99, it skips 97, it skips 94. So that there are all these big cookies that are available that it's skipping, okay? The greedy solution wouldn't do that, okay? The greedy cookie monster would just see that 99 and just reach for that first, okay? And you have these other solutions that are better at the end of the day, um, that actually um, are based on, that actually leave out those very large cookies. Okay, so any question about what's going on over here? So we looked at two variants of the problem where the obvious greedy strategy is perfect, okay? And now we looked at a slightly more constrained variant where the greedy algorithm doesn't do so well anymore, okay? And is really quite suboptimal. Okay. So here is the moral of the story, or one of the morals of the story. The greedy method does not always work, okay? And this is just like in real life, okay? Just doing the thing that seems to give the most immediate benefit is not something that is guaranteed to give you the best overall benefit, um, in the future as well. Okay, it's quite possible that the greedy choice you make now makes life harder for you later on, okay, or removes options further down the line. So for some problems, a greedy strategy works well. For other problems, it doesn't, okay? And so when we're trying to look for a greedy solution, one of the things that we always try to do is to look for counterexamples. Okay, so that's a big part of greedy algorithm design, coming up with a greedy strategy, and then trying to think about counterexamples. Are there instances in which this strategy would do something wrong? Okay. Now, if we can't find counterexamples, so we try and try, and if we can't find a counterexample, then we say, oh, okay, well, maybe the strategy is correct. Okay. And then we have to prove that the greedy algorithm is correct. And and we'll look at a bunch of ways of doing this. Okay. Okay. So the other thing is that in general, there'll be many greedy strategies. Okay. There will be many ways to maximize the immediate benefit. Okay. And so there won't just be one greedy algorithm. There'll be many greedy algorithms. And often you just try many possibilities and you say, okay, well, let's try this greedy strategy. Oh, here's a counterexample that shows it's bad. Let's try another greedy strategy. Oh, here's a counterexample that shows it's bad. And finally, you either go through the list and you never find a greedy strategy that works, or you eventually hit upon something that really does seem like it works. Okay. Okay, so any questions about any of this so far? Okay, so then we are going to move on to a greedy scheduling problem, to an interval scheduling problem for which we will try to find a greedy solution. Does the greedy algorithm take less time sometimes? Yeah, so one of the motivations for looking for greedy solutions is that very often they're very efficient. Okay, so yeah. Okay, so let's move to the next bunch of slides. Okay. Great. Okay, so here's a question from Alec. To solve that last problem, okay, yeah, so how do we solve that problem? Okay, the problem where you're only allowed to take one cookie from each row and each column. Can you sum the rows and columns and pick the highest number from the row and the column with the minimum sum? Okay, so great. Okay, so this is another suggested solution. Okay, so you look at the sum of each row, you look at the sum of each column, and okay, right. So that's actually maybe a slightly more sophisticated greedy strategy. Okay, where again you try, use some criterion for picking a cookie, but then you fix it. Okay, and uh, and then you move on to the next cookie. Okay, yeah. So that particular problem, the one where you're only allowed one per row and column, um, is actually a kind of problem that we'll be looking at a little later in the class. It's called a matching problem. You can imagine a graph, a bipartite graph, which has 6 nodes on the left for each of the rows and 6 nodes on the right for each of the columns. And then there's an edge between a row and column, which gives the weight of the cookie for that row and column. Okay, so it's 6 on the left rows, 6 on the right columns, and it's a bipartite, fully connected graph. Okay, so there's an edge between every row and column, and the weight of the edge is the size of the cookie. Okay, and you want to find a matching of maximum weight. So we'll be looking at problems like that a little bit later in the class, and we'll be the sort of solution strategies that we'll be developing can be thought of as hill climbing or local search strategies. Okay, great. So let's move on to another problem now, and this is an event scheduling problem. Okay, so you are running a conference. It's a cookie conference, in fact, and there are a whole bunch of events that you want to schedule. And each event, okay, so you have a bunch of events, a collection of events, and each has got a start time and a finish time. Okay, so for example, you have an event that says that there's an event that wants to run from, let's say, 8 a.m. to 11 a.m. The problem is that you only have one conference room. So at any given time, you can only have one event taking place, and you have all these possible events. So you want to schedule the most events possible, okay? And what the constraint is that 2 events cannot overlap. So here's an example of what this would look like. So this is event 1. This is event number 2. So event number 1 starts at 2 and ends at 22. So it starts at 2 in the morning, it starts at 2 a.m. and ends at 2200 hours, let's say 10 p.m. And we can represent it just as an interval, 2, 22. Event number 2 starts at 3 and ends at 11. So we can represent it by an interval 3, 11, and so on. Okay. So there are all these events, and they all want to be scheduled. Okay, so these are each of these events is organized by some group, and every group wants that event to be scheduled. But we only have one room. Okay, so we cannot possibly schedule all of these events. Okay, so how many do you think we can do? So let's see. Here's a question by Andres. Does anyone know if these slides? Yeah, so these are called day 10 slides. It's day 9 today, so it's a little ahead of time, but we got through the day 9 slides, pretty expeditiously. After lecture, I'll be posting the annotated versions. Yeah, so this is the next slide deck, exactly. Okay, great. Now we want to schedule as many events as we can. How many do you think we can do? Okay, so Nguyen is saying 4. Can you tell me what the 4 are? What are the how can we do 4 events over here? What are the 4 events? You can refer to each event as an interval. So can you tell me what the 4 events are? Okay, so okay, so 3, 12. Okay, so let's see, 3, 12, 12, 16. So 3, 12, 12, 16, 16, 20. Yes, excellent. So 3, 12, 12, 16, 16, 20, and 20, 40. Excellent. Okay, so we can schedule 4 events. Is this the best possible? Is something better possible? I'm not sure. I don't see it, but I'm not sure. Okay. So any questions so far? Does it make sense what this problem is? Okay, so this is an event scheduling problem. And we'll be looking at a lot of different scheduling problems in the next lecture or two. Okay, so let's go ahead and formalize this problem. So let's say we have a collection of n events given by start and finish times. Okay, and we can represent them like this. Okay, so we'll say the start time of the first event and the finish time, the start time of the second event and finish time, the start time of the third event and finish time, and so on, all the way to the nth event. Okay, so our inputs consist of these n intervals. Now the solution format is some subset of the events. Okay, and the constraints are that the intervals in S cannot overlap. And what we want to do is to maximize the number of events chosen. Any questions about that part? So we've taken our problem. We've taken a problem for which we had, just an English description. And now we've written it down in the standard template that we are getting used to. So any questions about this way of writing down the problem that we had in mind? Does it make sense? So we've used this notation, S1, F1, and so on. Each event is just given by a start and finish. Okay, it's given as an interval of the line. We want to pick some subset of the events, and we want that subset to be as large as possible, subject to the constraint that the events cannot overlap. So here's a question. Can we translate it to a graph problem? Okay, so that's, Right, so that's interesting. Yeah, how might we write this as a graph, right? What do you think? If we wanted to write this as a graph problem, how many nodes should we use as a function of n? N, okay. So we can use one node per event. And what would an edge mean then? Okay, so Nguyen is saying, why don't we put an edge if two events don't overlap? In other words, if two events are compatible with each other, right? And then what are we looking for? We want to find a subset of nodes, and what is the property we need that subset to possess? What edges should be present within that subset? Okay. Yeah, so if we put an edge, if events don't overlap, okay, what needs to happen for that subset of nodes? What edges should there be between them? We want all edges to be present, okay? It needs to be complete. And you know what that's called? It's called a clique. Okay, so a subset of nodes such that there are all possible edges between them is called a clique. And so if we were to write it that way, the problem would be what would be called the maximum clique problem in a graph. Okay, does that make sense? And that is a hard problem. Maximum number of nodes that can create a complete graph, exactly. Okay, so that's a nice idea to make a graph out of it. That's a very sort of computer science impulse, right? We take our problem and let's see what happens if we write it as a graph. Maybe it translates to a standard graph problem. And in fact, it does. Okay, it does translate to a standard graph problem. But unfortunately, that problem is one that is computationally intractable. Okay, it's one of these classic NP hard problems. Great. So here we're going to adopt a different strategy and we're going to try and solve it using a greedy algorithm. Okay, so any questions so far? So we've talked about a problem, we looked at a little example, and now we've formalized it. Okay. Okay. So we have these n events, and we want to find a subset of events, okay, that don't overlap, and we want this subset to be as large as possible, okay? So the search space consists of all possible subsets. How large is that? Okay, so search space has size what? Two to the n. So let me see, there's a question. Here's a question by Alec. What if the edges are for nodes that do overlap? Yes, so getting back to that graph construction, suppose we create a node for each event, and then we we put an edge between two events if they do clash with each other. So now what we want is a set of nodes that contain no edges, and that's called an independent set. So we want to find the largest independent set in that graph. That is unfortunately another intractable problem. Okay, so that particular reduction is correct. It's true that the problem can be, if we had an algorithm to solve the click problem or the independent set problem, we could reduce our problem to that. But we don't have algorithms for those problems. Okay, great. Okay, so here we have this problem, and the search space is exponential. Okay, so the number of subsets, if we were to just look at all possible subsets of events, there are 2 to the n subsets. Why is that? Any questions about that? Why are there 2 to the n possible subsets, 2 to the n solutions that we would need to check? Okay, so we have these n events, and for each event, we can either take it or leave it. Right, so Dadian has put it well, that either we have these n events, and each one, take it or leave it. So we got 2 choices, take or leave, take or leave. Okay, so it's 2 times 2 times 2 times 2, so we get 2 to the n possibilities. And one way to try and solve this problem is to say, well, the search space is of size 2 to the n. Let's just look at all possible subsets. And for each subset, we'll see if it's valid. Okay, so each subset is a collection of events. We'll go through it and we'll see, can we do this? Do these events overlap at all? Okay, if they're non-overlapping, that's a viable solution. Okay, and just go through all of them and then pick the biggest subset that is actually viable. So is that a good algorithm? Is that a correct algorithm? Yes. Is it a good algorithm? Not very appealing, okay, because it is exponential time. Okay, so let's see if we can solve this problem using a greedy approach. Okay, so exponential is too slow. Let's think of a greedy approach. So we have these n events, okay? Can you suggest a greedy strategy? Okay, so now rather than looking at an entire subset of events, okay, rather than constructing an entire subset in one go, we're going to do something greedy. We're going to pick one event that looks good, that satisfies some greedy criterion. Okay, so we're going to pick one event that says, okay, let's just pick an event, that seems good in some way, fix it, then pick the next event, and so on. Okay, so let's look at some solutions. Pick the event with the least time interval. Okay, so pick event of shortest duration. That kind of makes sense, right? Because if there's a short event, then that seems reasonable. Okay, it's only going to use up, half an hour or an hour. That's great. So just pick something like that. Pick the event that ends earliest. Okay, so in each case, we're just going to say, what is the next event we should pick? Okay, so we're going to pick events one at a time. Okay, so one strategy is just always pick the one of shortest duration. So you pick the shortest one, then you pick the next shortest one that's still available, then pick the next shortest one that's still available. Okay, so let's see. Patrick is saying pick event that ends earliest. Okay, Paolo is saying pick events that are back to back. Okay, so what we want to do though is we want to say, how should we pick the next event? Okay, so we've picked a bunch of events so far. We're going to set them in stone. Okay, we're not going to go back and change those. What should be the criterion for picking the next event? Okay, so if we wanted to say back to back, we could say pick the next event to be something that starts as soon as possible, after one of the existing events. That's one way we could say it. Okay, so pick event that starts as soon as possible after events already chosen. Okay, so that's how we would say that. So that's a good suggestion. And so we would say we just need to phrase it in a way that tells us what is the specific criterion for picking the next event. Any other any other ideas for what we might do, for what would be a reasonable greedy strategy to try out? Okay, great. Okay, so so you can see that for a problem like this, there isn't just one natural greedy strategy, there's a whole bunch of them. Okay, and so what we would typically do is write down a few and then try them out and see whether they seem to work. Okay, so okay, so here are some that we've written down. Shortest duration. Okay, so that is something that one of you suggested. Earliest start time, pick the one that starts as soon as possible. I think that is basically Paolo's suggestion. Okay, pick the one that starts as soon as possible because you don't want to waste any time. Pick the one with the fewest conflicts. Okay, I don't think anybody suggested that. And pick the earliest end time. Okay, so the ones that you all suggested were these three. And there's another one here. Pick one that has fewest conflicts with other events. Okay. Okay, so these all sound like fairly sensible greedy strategies. Let's try them out, okay, and see what happens. So the event of shortest duration, what do you think? Okay, so what this will do is that for each event, it'll just compute how long the event takes. Is it 1 hour? Is it 4 hours? Is it 6 hours? And the first thing it'll choose is just the shortest event of all, okay? And then it'll move on to the next shortest event and so on, okay? So what do you think? Is this optimal or not optimal? Okay, right, okay, so there's some questions about conflicts. Okay, so what we're gonna do here is always gonna be the same. We're gonna pick the next event according to our greedy strategy, then remove any event that conflicts with this thing that we've chosen, and then pick again from those remaining according to our greedy strategy. So we're not worried about conflicts. Every time we pick an interval, we will remove anything that conflicts with it. Okay? Okay, so assuming that we're doing that, okay, so we pick the shortest event, we remove anything that conflicts with it, and then we pick the shortest out of what's remaining, remove anything that conflicts with it, and so on. What do you think? Is that optimal? Now, if it's not optimal, then there has to be a counterexample, okay? Because either it always works or there's an instance in which it doesn't work. Okay, so anytime it's not optimal, there has to be a counterexample. So James has suggested a nice counterexample. Okay, so let's do that. Okay, so here's a counterexample. So here we have three intervals. Okay, what is the best possible solution? How many intervals can we get in there? How many events can we get? We can get two of them, right? And what will the shortest duration thing do? What it'll do is it'll say, well, oh, the shortest duration is this, let's take that. And the minute you take that, it knocks out the other two. So here, the optimum solution, oops, here the opt has got two events and greedy just gives one event. And so we have a counterexample we have a counterexample that shows that this particular strategy is suboptimal. Okay, great. So Alec is saying, how about picking the one with the fewest collisions? And we'll look at that strategy, okay? And he's saying that this is closest to the independent set idea, okay? They're saying that, look, we talked about reducing this problem to both click or independent set. And maybe one way of solving independent set is to just start by picking the node with smallest degree. Okay, so we will look at that strategy very shortly. Okay. So Patrick is saying, what if we have events that start and end at the same time? Right. So in those cases, we can just immediately eliminate one of them, right? But he's saying that this will throw off anything that looks for the number of collisions. Okay. Yes. So let's get to that. Okay. So any questions first about shortest duration? So this was a very reasonable sounding greedy strategy, but it's not optimal. Okay. And the way we see it's not optimal is by constructing a counterexample. Okay. Earliest start time. Okay, so this is also one of the strategies that one of you suggested. And the idea here is don't waste any time. If the room is available, starting at 1 in the morning, start with start with the event that begins as close as possible to 1 a.m. Okay, so what do you think? Is this optimal or not? Okay, and once we pick an event, we'll remove anything that collides with it and then pick the earliest start time amongst those remaining. Okay, so Brett is saying you could have an event that goes all day. Great. Okay, so you could have one event that looks like this, and then you have these other events that look like this. And so the greedy algorithm ends up choosing this one event. It begins straight away, but it just lasts all day long, okay? And the optimal solution, so this is the greedy solution, oops. And this is the optimal solution. Okay? So questions about that. So again, this seems pretty reasonable. There's certainly, if you were trying to convince somebody of it, there are ways in which you could make it sound compelling. We don't want to waste any time. Let's just get started as soon as possible. But when it comes down to it, you could end up in a situation like this. Okay. And so Ken is saying, this is me on finals day. Okay. Okay, so any questions about why this is bad? Okay, and the way we know it's bad is that we've constructed a counterexample. Okay, it's not enough to say, I don't have a good feeling about this. You have to demonstrate an explicit counterexample. And the minute you have that, it shows, without a doubt, that the particular strategy is suboptimal. Okay. Okay. So now let's get to the greedy strategy that a bunch of you have been talking about, and that's fewest conflicts. Okay, this is kind of an interesting sounding one. Okay, so let's go back to our previous examples and see what would happen. What would fewest conflicts do over here? Would fewest conflicts give us the right answer in this case? Right, because how many conflicts does this guy have? How many conflicts does this interval have? It's only got one conflict, right? This only has one conflict, this has one conflict, and this has two conflicts. So fewest conflicts would be okay in this one. Okay, for this case, it would be okay. What about in this case? What would fewest conflicts do over here? Would it be okay? Yeah, let's see. So let's look at this big interval. How many conflicts does this have? It's got 11, right? It has 11 conflicts. And how many conflicts does this one have? It's only got one conflict. So we would end up picking one of the ones with one conflict, and that would be perfectly fine. So it would work in this case. Okay, great. So this is starting to seem promising. This particular strategy doesn't fall into the same trap as these other two strategies. Okay, so it sounds promising. Um, but I think that one of you already pointed out a possible issue. I think Patrick was saying that you can construct an example where you just duplicate a few, where you duplicate a few intervals, where you duplicate a few events, and therefore artificially boost the number of collisions, and this could trip it up. Okay, and so let's look at a counterexample of that form. So in this example, first of all, what's the optimal solution? How many events can you schedule in this example? Four. Very good. Okay. Now let's see what the fewest conflicts would do. How many conflicts does this guy have? 7 conflicts. Great. And this has 7 and this has 7. How many conflicts does this guy have? And I'm just thinking of conflicts as being the number of other intervals, the number of other events with which it overlaps. If you're if you're thinking about the graph, it's literally the degree. Okay, great. So this is 8, 8, 8, 8, 8. What about this one over here? Again, 8. Okay. What about this one over here? 4. Great. What about this one here? This is again 8. And this one is again 8. And these are again 7s. So which would it pick first? It would start by picking this. Or at least, at any rate, one of those 3. Okay. So any questions? So this is the first thing we'd do, right? Okay. Um, okay. Alec is saying some unflattering things about the algorithm. Um, so it would do 4, and then once it's picked that, okay, so once it's picked this, it would only be able to take one from the left and one from the right, and say that, and so it would get a solution of size 3. Okay, so in this case, the optimal is 4, and the greedy is 3. So Nguyen is saying, can we say it's suboptimal and call it a day? Yeah, so you say it's suboptimal, you show the counterexample, and then you move on. Okay? Okay, so any questions? Okay, so the best thing to do in this case is, for example, to take this one, this one, this one, and this one. That's 4, but greedy ends up taking 3. Okay? Okay, great. Okay. Alec is saying it did not mirror the independent set solution close enough. Yeah, so you could think about what this solution would be doing in terms of the underlying graph. Okay, if you where you have a node for each for each event, and you have edges between events that collide. Okay, and so what we're doing over here is to pick the one with the fewest collisions. Okay, so with the smallest degree, and then proceeding. Okay. Okay, so another possibility. Okay, so at this point, we've tried three greedy strategies, and we've managed to shoot down every single one of them. Okay, so there was another one that had been suggested, earliest finish time. Okay, let's see what would happen. So what would earliest finish time pick in this one? Yes, so earliest finish time would first choose this, and then it would choose this. Great, it works here. What would earliest finish time do over here? It would pick this, okay, because this is the one that finishes before any of the others, okay? So it would be okay over here. What would earliest finish time do over here? Well, it would pick this one basically, and then it would pick this one, and then would pick this. It would do the right thing over here. Okay, interesting. So earliest finish time is okay on these three examples. Does that mean it's optimal? No. Um, let's go back to our original example. What would earliest finish time, which interval would earliest finish time choose first? 311, yeah, so it would start by picking this, okay? And then it would say, okay, now we're gonna look to the right of this line. So which one would it pick next? 11:15, great, because that has the earliest finish time out of those remaining, okay? And then it would say, okay, we're now gonna look at the right of this line, so which one would it pick next? It would pick 16 to 20, great. Okay, and I will look to the right of this line, and then it would pick this. And so it would end up picking these four intervals. And that does, in fact, turn out to be the optimal solution in this case. Okay. Okay, so it seems to work. We have seen that it works on 4 examples. Does that mean it always works? No. The only way we can be sure it always works is by proving that. Okay? It turns out that this greedy strategy is in fact optimal. And we'll see how to prove that next time. Okay, so that's something we'll get to next time. So we went through all these strategies. We've come to this one strategy, and this one is something that we don't seem to be able to defeat. Okay, so we were trying various counterexamples. They don't seem to be working. And as you know, it deals successfully with one example after the next, we're getting more and more hopeful and excited that maybe this strategy is actually optimal. Okay, and at this point, um, we want to see if we can prove it. Okay, so next time we'll be talking about proving the optimality of a greedy algorithm. Okay, and we'll look at 2 or 3 different ways of doing that. Okay, so any last questions before we wrap up for today? Okay, so see you all on Thursday, and remember that this week's homework is a little harder than usual, and so you have a couple of extra days to do it. Okay, so you have until Friday. So just, take the time and, enjoy those problems. There's a lot to think about. Okay, see you all on Thursday.